Hello there, this is Jude Socrates. Welcome to today's video, which is about general exponential and logarithmic functions. So in the last couple of videos, we learned about first the natural logarithm function, and we saw that it was increasing. It is 1-to-1 with the domain 0 to infinity and range all real numbers. So from there, we were able to construct the natural exponential function. So guess what? Today we are going to combine those two functions to create general exponential functions and general logarithmic functions. So we have quite a laundry list of things to do today. So here is what we're going to get to in this video. So first we will try to understand, what does an exponential expression mean anyway? A number raised to another number in the exponent. What does that even mean? So from this basic idea, we will construct general exponential functions. We wrote the exponential function as e to the x before. So now we will write a to the x, where a is some arbitrary positive number. What are the properties of these functions? We will prove them, as well as their derivative and antiderivative formulas. So we're going to find out that these functions are 1-to-1. So they will have inverses. So the inverse of these exponential functions will naturally be called the logarithmic functions with the same base a. Okay, well, how do you compute these functions? We will prove what's called the change of base formula. Maybe you've heard of it from pre-calculus. And from this, we will find the derivative of these logarithmic functions. You may have noticed that we have not found an antiderivative for the logarithm function. And that's because we don't have the technique yet to do it. It will be coming very, very soon. Now, in a related construction, we will make what are called general power functions. Okay, so these should look familiar. We know what x squared and x cubed mean. What about x to the k, where k can be an irrational number, for example? What does that even mean? We will from here derive or generalize now the power rule for derivatives, which we learned all the way back from basic calculus. And that is the derivative of x to the k is k times x to the k minus 1. So you drop the power and then you decrease the power of x by 1. So we will finally be able to prove this when k is not a fraction, not a rational number, but it can be any real number. Recall that we had a video where we discussed a brief history of the power rule. We can now complete the proof of the power rule. And finally, we are going to go back to logarithmic differentiation. If you recall, we discussed this at the end of our video on the natural logarithmic function. So we will extend this to functions which are general exponential expressions. There will be a variable both in the base of the function as well as the exponent. Okay, so as a warm-up, let's take a look at these exponential expressions. Okay, we know what all of them mean. Okay, so let's review. What does 3 to the 4th power mean? Okay, so it means that you multiply 3 to itself 4 times. 3 times 3 times 3 times 3. So that is 9 times 9, which is, of course, 81. Okay, what if we flip it a little bit, and just for good measure, let's put a minus sign in the exponent. So that minus sign tells us we are now dealing with a reciprocal. So it's 1 over something. But our base is 4, and the power will now be 3 in the denominator. So that means that we multiply 4 to itself 3 times. Okay, so that is 16 times 4. So that is just 1 over 64. Okay, so that is the meaning of 4 to the minus 3. Okay, what about the power of 0? Okay. So you probably know that the answer is 1. Why is it 1? Well, it's because, check it out over here. We have 3 to the 4th power, 3 appearing 4 times. So you can think of this as 3 to the 3rd power times 3. Okay, so it means that if you want the fourth power, you start with the third power and then you multiply by another 3. So this works backwards. If you want the third power, you start with 3 to the 4 and you divide by 3. Okay, so how about the 0th power? Well, start with the first power of 7 and you divide by 7. Okay, but 7 to the first power is simply 7. 7 divided by 7. That's where we get our 1. Okay, so now what about fractions? Negative 8 to the power 1/3. Okay, so what is that? You probably know that the answer is negative 2. But why is it negative 2? So let's call it something. It's a number y, which means that y to the power 3 is negative 8. Okay, so the 1/3 power comes as the inverse of the cubic function. Okay, so we want to know what number, when you multiply it to itself 3 times, will give you negative 8. And of course, the answer is negative 2. Minus 2 times minus 2 times minus 2 gives you minus 8. Okay, and there's no other possibility because y cubed is a one-to-one function. Okay, so all that for simple minus 8 to the 1/3, that should be a minus 2. Okay, so now that we've seen it, we should probably write that because minus 2 times minus 2 times minus 2 is minus 8. Okay, y to the 5/2. So this is now a more complicated fraction. So we can think of it as, well, let's take y to the 1/2, 9 to the 1/2 first. So let's make a copy of that. And then we will take the whole fraction to the power 5. Okay, so we are working with the assumption that the exponents satisfy certain rules. Okay, so in other words, if you have two exponents here, they should multiply together into a single exponent. Okay, why does that even work? Okay, so 9 to the 1/2, we know that that is 3. 3 raised to the power 5. 3 multiplied by itself 5 times, this is 4 times another 3, you get 243. Okay. But what about 5 to the power pi? I mean, you know, so pi is no longer a rational number. In fact, it's a transcendental number. It's even worse than one of the worst irrational numbers, but we love it. What does that even mean? Okay, so, well, as a first step, let's assume that it is a number. Okay, that's actually a very big assumption. Okay, why should that expression even make any sense? Okay, so in a minute, of course, we will see that we can make it make sense. Okay, so let's give it a name. Let's say that y equals pi to the power 5, and let's try to solve for y. Okay, so y equals 5 to the power pi. And what can we do? Well, we can take the natural logarithm of both sides of the equation. So we have ln of y on one side and ln of 5 to the pi on the other side. Okay, but I hope you remember your rules for ln. Okay, we said that ln of a to the x, some number to a power, we just drop the power. Okay, so that's pi ln of 5. Okay, so that's ln of y, and okay, well, we know what ln of 5 is. We know that that's a number. We can multiply by pi, that's another number. Okay, we're looking for y, so y will be e to the power pi ln of 5. Okay, so yeah, so we did a few, we took a few liberties here. Okay, why does 5 to the pi even make any sense? Okay, but if it does, then we can take the ln of both sides. We can drop the exponent. Does that even work? Didn't we say that the exponent has to be a rational number? So yeah, that's another liberty that we took there. So yeah, we can take, we can compute that and raise it that will be the exponent of e. Okay, so yeah, of course, we can ask Maple, oh, great Maple, what is that number? It's about 156.992. Okay, would Maple have computed this directly? Well, it's probably very smart. So yeah, it gives just about the same answer. Okay, so we want to generalize this process. So that's what we're going to do next. All right, so we want to define a general exponential expression, a to the power b. Okay, so to make it make sense, we will restrict a to be positive, but b can be any real number. All right, so why do we need a to be positive? Well, because we're going to use the cancellation property for e to the x and ln of x. Okay? If you take e to the ln of a, you get back a. All right, but for this to make sense, a has to be positive to begin with. Okay, but we also have the power rule. E to the x to the power r is e to the x times r. Okay, and when we did this, we said that r has to be a rational number. Okay, because we only know how to take a rational exponent for a real number. Okay, so now we want to address the possibility that what if that exponent is not rational? Okay, so we have these two steps, so we can now rewrite a to the b, oh, my apologies, that's an r. Okay, so let's turn that into a b. A to the b is e to the ln of a times b. Okay, and no, I'm sorry, it is r. Okay, because at this point we only have r to be a rational number. Okay, so if r is a rational number, then a to the r is e to the ln of a to the rth power, and that is simplifiable to e to the ln of a times r. Okay, but now what if r is irrational? Okay, well, we can still multiply ln of a times r. That's still a number. And we know that e to the x is defined for any real numbers. Okay, so this expression makes sense even if r is irrational. All right, so here's our generalization. Suppose that a is a positive real number and b is any real number. We will define the expression a to the b, which we will call a general exponential expression. We will use the formula a to the b will be e to the power ln of a times b. Okay, so take the ln of the base a, multiply to the exponent b, and that will be the input to the function e to the x. Okay, so let's take a look at pi to the square root of 2. Okay, a different expression from what we had last time. Okay, so according to our definition, we have this meaning for a to the b. We want to find the decimal approximation for this number, just like we did for, what was it, 5 to the pi. Okay, so the instruction says, first get ln of the base, ln of pi. Okay, so you can do this on your calculator. We'll get about that much. Okay, and now we multiply by square root of 2. Okay, so ln of pi times square root of 2. Let's borrow that square root of 2 up here. Okay, so that will be approximately, so I apologize that that is a hard equals sign when it should be an approximation. Okay, so we'll multiply those two numbers today, now. And what do we get? Okay, let me highlight that and whoops. Okay, I had some invisible characters in there, which I had to erase. Now let's compute. Okay, now it works. So that will be our input to the exponential function. So our last step is e to the power 1.618 blah, blah, blah. Okay, so we input that into our e, and Maple says it's about this much. Okay, so you could also try, I mean, I'm not going to lie to you, you can try to input this directly into your scientific calculator. Okay, you probably have a key that says x to the y or y to the x. Okay, so this should be the correct answer. So try it out on your scientific calculator. See if you get the same answer. Okay, can Maple do this directly? Oh, there it is again. Let me erase the invisibles. Okay, and let's try again. Yeah, there you go. So we get exactly, well, approximately the same answer. Okay, that last digit is a 7, that's a 6. Big deal. All right, so now let's use this idea to construct general exponential functions. Okay, so we said that a to the b is defined to be e to the power ln of a times b. Whether or not b is rational, could be irrational, it doesn't matter anymore. Okay, but we will fix our base a to be a positive real number because we will need its ln. Okay, so we will define the general exponential function with base a to be notated as a to the x. It will be defined as e to the power ln of a times x. Okay, so x can be any real number, and as we're about to see, the range will be 0 to infinity, just like e to the x, because that is the parent function of our general exponential function. Okay, we also saw that if we graphed e to the 3x, e to the minus 4x, if I'm not mistaken, we saw that e to the 3x is increasing, so the coefficient of x is positive, so it kind of looks like this. Oh, I'm doing it correctly this time. I was doing it backwards in a previous video, and it is monotonic decreasing if k is negative. Okay, so this time it's going like that. Okay, or like this. Okay, so that's because, so let's apply this now to these two examples. We're going to look at 5/3 to the x and 2/3 to the x. Okay, so we will classify them as either increasing or decreasing, and we will look at their graphs in GeoGebra. Okay, we can do the first thing right now because according to the definition, 5/3 to the x is e to the ln of 5/3 times x. Okay, so we will replace a with 5/3. Okay, but what do we know about ln of 5/3? 5/3 is bigger than 1. So ln of 5/3 is a positive number. Okay, so the coefficient of x is positive. We therefore get an increasing function. Okay, so this is increasing because ln of 5/3 is positive. Okay, so how about 2/3 to the x? So we will now get e to the ln of 2/3 times x. So we'll change that 5 to a 2. This time, 2/3 is smaller than 1. So ln of 2/3 is now negative. We get a decreasing function. It's decreasing because ln of 2/3 is less than 0. Okay, so let us graph these two functions in GeoGebra. We will verify that they are increasing and decreasing respectively, and we will also be able to verify that the range is from 0 to infinity. All right, so we have 5/3 to the x, up arrow x. Woohoo, there it is. Okay, so we do get an increasing function. We never touch the x-axis because e to the something is always positive. And of course, this is going up to infinity. Okay, so how about now 2/3 to the x? 2/3 to the x now looks like this. So this time it is a decreasing function, and the range is still from 0 to infinity. Okay, let's now take a look at some properties of exponential functions, which you hopefully remember from pre-calculus. Okay, so if we have two positive numbers a and b, we will have two different bases. And we can have any two real numbers, x and y. Okay, so if you're in the exponent, you're safe. Okay, you can be positive, you can be negative, 0. It's all good. All right, so a to the x plus y is the same as a to the x times a to the y. A to the x minus y is the same as a to the x divided by a to the y. A to the x raised to the power y is a to the x times y. And a times b to the power x is the same as a to the x times b to the x. A over b to the x is the same as a to the x over b to the x. Okay, so we certainly see this in pre-calculus, but we developed our functions in a different way. Okay, so in particular, these properties work for e to the x. Okay, so before we said that e to the x to the r is e to the x times r. Okay, but now that we have our general functions, this property still works even if y is irrational. Okay, so e to the x to the power y is the same as e to the x times y. Okay, we also want to warn you that if you see an exponential expression like this with a coefficient, it means that you're multiplying a to the expression b to the x. Okay, it's not a times b to the x. So if you see 3 times 5 to the x, you don't get 15 to the x. Okay, this simply means, if you want to be explicit about it, 3 times 5 to the x. Okay, so to avoid confusion, this is actually how I would be writing, or use parentheses to be safe. Okay, so to me, this is the most interesting property because now we know that it works even if y is irrational. See, x and y can be any two real numbers, rational or irrational. Okay, so why does this work? Well, we said that a to the b is e to the power ln of a times b. Okay, so let's start inside. A to the x means e to the power ln of a times x. That should be an a times x. Okay, and then we raise to the power y. Okay, all right. However, we have another exponential expression here. Okay, so think of this now as some number raised to the power y. Okay, so let's give it a name. Let's call it c to the power of y. Okay, where c is this thing over here, e to the ln of a times x. Okay, but we now have c to the y, so let's apply the same principle. C to the y is, according to our formula here, we get e to the power ln of c times y. Okay, times y. All right, but, well, c is this thing. So what is ln of c? Okay, so we want ln of e to the ln of a times x. Oh, wait a minute. We have cancellation properties. Ln of e to the something takes you back to that something. So we're back to ln of a times x. All right. So ln of c is just ln of a times x. Okay, so we have used that. We don't need it anymore. So where are we? Let's bring this back up to c to the y. And we said that c to the y is e to the ln of c times y. But ln of c is ln of a times x. Okay, so we have one more step. Ln of c is ln of a times x. So we replace ln of c with ln of a times x. There we go. Okay, but wait a minute. We have e to the ln of a times x times y. How do we define a power function? Okay, so it was over here. We said a to the x is ln of a, e to the ln of a times x. Okay, so let's bring that down here. A to the x is e to the ln of a times x. We have x times y here instead of just x. So this is equal to a to the power x times y. Aha. So x times y is also a real number. So this means we are taking a to the power x times y. And that's exactly what this property is saying. Okay, time to do some calculus. We want to find the derivative of a to the x, our general exponential function. Okay, but a to the x can be written in terms of e and the ln function. Okay, so we said that the derivative of e to the x is simply e to the x. Okay, but we don't have e to the x, we have e to the something times x. So we apply the chain rule. The derivative of e to the ln of a times x is the same thing, e to the ln of a times x, but by the chain rule, we have to multiply by the derivative of ln of a times x with respect to x. Okay, I want to point out something very important. X appears only once in this product. Okay, that's ln of a. It's not ln of x. Okay, in other words, ln of a is just a constant. Okay, you don't use the product rule. You simply use the constant multiple rule. Okay, so this is simply ln of a times the derivative of x, which is just 1. So all we get is ln of a. Okay. Oh, however, there is still this part. This part does not go away. There we go. It looks better there. So we get ln of a times e to the ln of a times x. Oh, but wait, there's more. E to the ln of a times x is simply a to the x. Okay, so we can rewrite this. Let's do it on the next slide. As ln of a times a to the x. Okay. So if you want the derivative of a to the x, you simply keep a to the x, just like we did for e to the x. But there's an extra factor of ln of a. Okay, so let's highlight that. Okay, the derivative with respect to x of a to the x is ln of a times a to the x. Okay, there we go. So it's just like e to the x, except there's an extra ln of a factor here. Does that apply also to e to the x? So if it were derivative of e to the x, we'll get e to the x ln of e. But wait a minute, ln of e is 1. Okay, so we get exactly the same formula. Okay, what are the derivatives of 5/3 to the x and 2/3 to the x? Okay. So for 5/3 to the x, we get ln of 5/3 times 5/3 to the x. Okay, so we just multiply ln of 5/3 by 5/3 to the x. And what does this tell us? Whoops, I'm sorry. So this is the derivative, not f of x. We want the derivative of 5/3 to the x. Okay, so there you go. What does this derivative tell us? Well, we already know that 5/3 to the x is always positive, okay, because it comes from e to the ln of 5/3 x. We're multiplying by ln of 5/3, okay? And again, we said that 5/3 is bigger than 1, so ln of 5/3 is positive. So therefore, our first derivative is a positive number for any x, okay? The first derivative test tells us that our function should be increasing. And that's what we saw in GeoGebra. It was increasing as we move left to right. Okay, so similarly for g of x, the derivative of 2/3 to the x, you know what? I would just copy up to here. The derivative of 2/3 to the x is ln of 2/3 times 2/3 to the x. Okay, and now ln of 2/3 is negative because 2/3 is smaller than 1. 2/3 to the x is still always positive. So we're multiplying a negative by positive. This time we get a negative number. So by the first derivative test, our function should be decreasing, and that's what we verified. All right, now anytime you have a derivative formula, you have as a bonus an antiderivative formula, okay? However, on the right side, a to the x has a friend with it, an ln of a. We would like a to the x to be by itself, okay? So we will divide both sides by ln of a. And again, we have a constant multiple formula for derivatives. So if you multiply both sides by 1 over ln of a, then the right side will now be by itself, and the ln of a will be on the left as a reciprocal. Okay? Again, that's just a constant. Okay, so there's no product rule to worry about. So because we have that as our derivative, we will get the antiderivative formula, which tells us that an antiderivative for a to the x dx will be 1 over ln of a times a to the x plus c. Okay. So yeah, it's going to get a little bit confusing. When do you multiply by ln of a? When do you divide by ln of a? Practice, 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 like everything else in math, okay, to help you remember these formulas. Okay, so now what is the antiderivative? What is an antiderivative for 5/3 to the x? Okay, so according to our formula, you just get 5/3 to the x, but you divide by ln of 5/3. Okay, so we will copy this. We want ln of 5/3 in the denominator, multiplied by 5/3 to the x plus c. Okay, do you have to do anything about ln of 5/3? Well, it's ln of 5 minus ln of 3, but does that really help? No, you're better off just keeping them together. All right, so now that we understand general exponential functions, we're going to invert them. Okay, so we saw that 5/3 to the x was increasing, but 2/3 to the x is decreasing. Either way, they're 1 to 1. Okay, so they have an inverse function, and recall that for an inverse function, you exchange the roles of x and y. Okay, so let's give the inverse a name. Let's call it g of x, as we traditionally have done in the past. So that will be written as the logarithm to the base a of x. Okay, so the domain is now the range of f of x, which is 0 to infinity, and the range is now going to be the domain of f of x, which is all real numbers. Okay, so it's almost like we went full circle, actually. Notice that we started with ln of x, then we made e to the x, and then from these two, we made a to the x, and now we're back to logarithms, log base a to the x, the circle of life. Okay, what is the relationship between these two functions? So again, when you create the inverse, you exchange the roles of x and y. So y equals log base a of x means that a to the power y must give you x. Okay, so to understand this system, you ask, what is the power of a that will give me x? Okay, now, if you look at your scientific calculator, right, here's mine, there are two buttons. Here we are. In my case, I have log and ln on my scientific calculator, but if you want logarithm base 5, you're out of luck. Okay? The calculator doesn't have a logarithm button for every number, every positive number. So our next goal is to help us to compute these numbers. Okay, so we want a way to compute logarithm to any base of x, okay? Using our scientific calculator, if possible. Right, but again, that means that a to the y equals x, okay? So we want to know, how can we get y, okay? Well, our usual trick. Let's apply ln to both sides of this equation. So ln of a to the y equals ln of x, okay? But now we have the power rule, exponent rule, which says that, okay, I can drop that y. We get y times ln of a equals ln of x. Okay, so now solving for y, we get y must be ln of x divided by ln of a. All right, so that is our log base a of x. Okay, so let's highlight that. Log base a of x is exactly the same as ln of x divided by ln of a. Okay, so now you can use the ln button in your calculator to compute this. By the way, that log button, which is probably in your calculator as well, is logarithm to the base 10. Okay, so it's useful for some scientific applications. So approximate log 5/3 of 7 using this formula. So what do we want? We want in the numerator ln of 7, and in the denominator we want ln of 5/3. Okay, now I want to make this perfectly clear. You don't divide the 7 and then 5/3 first, okay, before you do the ln, okay? Think of it as order of operations. Okay, in the numerator you want ln of 7, in the denominator you want ln of 5/3. Okay, so you do them separately. Okay? You might have to write something down, or maybe you know how to use the memory on your calculator. Okay, so let's start with ln of 7. What is ln of 7? According to Maple, it's about 1.946. And what is ln of 5/3? It is approximately 0.5. Okay, so we put those two numbers in our fraction. This is our numerator, and this is our denominator. Okay, so we divide that, and we get approximately 3.8093. Okay, so that is log base 5/3 of 7. Okay, so we said earlier that the logarithm is really an exponent. What should be the exponent of a so that you will get back x? What is inside our logarithm function? The argument, okay? So this tells us that starting with the base 5/3, if we raise 5/3 to this power, okay, so what if we got lazy and we just said 3.81? Okay, we'll just approximate it. We should get something which is close to 7. So what do you say? Ooh, 7.002. Okay, so that round off, it's, 002. That's a little way off. So 0.93. Do we get a better answer than that? Okay, what do we got? Ooh, so yeah. So now it's a little bit smaller than 7, but it looks like it's a little bit closer as well. Okay, so now we are going to use that change of base formula. We have this over here. To graph 5/3 to the x, GeoGebra can do that. We will use this formula to graph the inverse function. And we're back. So I just deleted the 2/3 to the x, which we don't need. What we do need is log base 5/3 to the x. Log base 5/3 of x. Okay. So we said that the change of base formula says we just need ln of x and divide by the ln of 5/3. 5/3. There you are. So that is the inverse function of 5/3 to the x. Okay, so are they mirror images? Let's draw our y equals x. Yeah, that looks right. Okay, so just like what happened to ln of x and e to the x, these two functions are symmetric across y equals x. Okay, you can tell here that they are, yeah, just almost perfect mirror images of each other. All right, so our next task is to find the derivative of a general logarithmic function. What does it mean? Well, we said that we have a nice change of base formula. It's just ln of x divided by ln of a. Okay? So if you want the derivative, d by dx of log base a of x, it's simply the same as the derivative of ln of x over ln of a. Okay? One more time. ln of a is a constant. There is no x in this expression. Okay? A is fixed. X is only here in the ln of x. Right? So we can factor out the ln of a as 1 over ln of a times the derivative of ln of x. Okay? And I hope you remember the derivative of ln of x is 1 over x. Okay? So we get 1 over ln of a times 1 over x. And if you like, we can put those two together. Okay? Where should we put it? Well, it's probably safer to put the x to the left. Okay? Usually we put the coefficient, the constant on the left. But in this case, it is so tempting to put, if you put the x on the right, so tempting to put x inside there, it doesn't belong in there. Okay, ln of a is by itself multiplied to x. Okay. All right, so here's our problem. Let's look at logarithm to the base 5 of this quadratic, 3x squared minus 7x plus 4. Find the derivative. Okay, so according to our formula, derivative of log 5 is 1 over whatever is in here times ln of 5. Okay, so 1 over ln, 1 over whatever is in there, so I'll make a copy of this, times ln of the base 5. However, there's more. Okay, we also have the chain rule. Okay, so we need to multiply by the derivative of what is inside, which is 3x squared minus 7x plus 4. Okay, so that's just the power rule, basic form, 6x minus 7. Okay, so that can go simply in the numerator of our fractions so far. We get 6x minus 7 divided by this. Okay, and again, do you need to do anything about the ln of 5? Nah, just leave it there. It's fine. Okay, so in an exponential function, the base is fixed, our a, but the exponent is x. Okay? In what we're about to do next, we're going to switch it. Okay? So x will be a positive real number. It will be found in the base of our exponential expression. The exponent will be a fixed real number. Okay? So you've obviously seen this before, except you usually see x squared, x cubed, or x to the minus 5, or x to the 2/3. Okay? But this time, k can be an irrational number. Okay? So in our exponent, we're going to do x to the square root of 2. What does that even mean? This is what it means. Okay? So we can now give meaning to the expression x to the power k using exactly the same idea that we started with. It all goes back to this definition we made at the beginning of the video. So a to the b is e to the ln of a times b. So x to the k is e to the ln of x, the base, times k. Okay? So in our function, we have x to the square root of 2 we can rewrite it as e to the power ln of x times square root of 2. Okay, so when Maple calls up a radical, it puts an index. Okay, if you cut it out and then repaste, it'll look fine. Okay, so let's go to GeoGebra and look at this graph. Will it look like x squared? Will it look like x to the 1/2? We shall see. Okay, so we want x to the square root of 2, and we said that it is e to the power ln of x times square root of 2. So we can write that as 2 to the power 1/2. Ooh, there we go. So that is the graph of x to the square root of 2. Okay, does it look like x squared? I don't think so. Would you say it's like x squared? Not really. How about x to the 1/2? 1/2 and delete that. Ugh, even worse. So neither. Okay. Well, that's because square root of 2 is about 1.414235. Okay. So if anything, x will look x to the square root of 2 will look more like x to the 1.4. Ooh, there you go. See how close they are to each other. Hide, hang on, there you go. Hide, and it's there. See, they are so close to each other near the origin. As you go further out, yeah, they separate a little bit. Okay, so if you add more digits, 1.41, boom, ooh, you can hardly tell that apart now. Okay, so yeah, it's not close to x squared, it's more close to x to the 1.41. All right, so now that we have a meaning to x to the square root of 2, let's go back now to properties of exponents that we've seen since back in algebra. Okay, so x to the a times x to the b is x to the a plus b. You add the exponents together. X to the a over x to the b, you subtract the exponents. Okay, so by the way, here x is positive, and when there is a second base, that should also be positive. So x and y are both positive in these properties. Now we have two bases with the same exponent. X to the a times y to the a is the same as x times y to the a. X divided by y, x to the a over y to the a is x divided by y, all raised to the power a. And finally, x to the a raised to the power b is x to the a times e. So this is kind of similar to what we saw for exponential functions, where we had a to the x times to the y is the same as a to the x times y. Okay? And again, everything goes back to how we define an exponential expression. Okay? So in our case, we're looking at x to the something. Let's do the third property. Okay? So we have x to the a and y to the a multiplied together. Okay? So we said that x to the k is e to the ln of x times k. So we want to show that this product is the same as xy quantity to the power a. Okay, so we want x to the a. All right, so yeah, let's copy both of these and replace them one at a time. So x to the a times y to the a. So we will need this recipe, except instead of k, we will have a. Whoops, try that again. Instead of k, we will have a. All right, there we go. Now we need y to the a, so it will be the same as x to the a, except we want ln of y instead of ln of x. And there we go. Okay, but now we have u to the something times, e to the something times e to something else. Okay, we have e to the u times e to the v. But we said that we have a property for that. We have e to the u, and then we have to add the second exponent. Okay, so we'll take this, and we will add ln of y times a. Okay, so we use the property of the exponential functions. Wait a minute, there's a common factor of a in that exponent. Okay, so we can factor it out, and we can put these two in parentheses, except we should delete the other a over here. Okay, times a. Yeah, there you go. Okay, so we have e to the quantity ln of x plus ln of y. Remove that dot, times a. Okay, but we have another property. We know that ln of x plus ln of y is the same as ln of x times y. Okay, so we can change this to ln of x times y. Okay, I'm not going to put a dot in between. Okay, there we go. So we have e to the power ln of xy together times a. Okay, but wait a minute. E to the ln of x times k is x to the k, but it looks a lot like that, except instead of x, it's xy. So replace x with xy, replace this x with xy as well. So this is the same as x times y raised to the power a. All right, there we go. So that is the third property. Of course, the other four properties are proven using very similar ideas. All right, so now that we understand what x to the square root of 2 is supposed to mean, we can get formulas for for the derivative of x to any power, including square root of 2. So again, it's exactly the same formula that we see in 5a, which is why they said, go ahead, memorize this. It works no matter what your exponent is. Now we will know why it really works. Okay, drop the exponent and subtract 1 from the exponent. Okay, why does that work? Well, remember that this is the meaning of x to the k. All right, so if you want the derivative of x to the k, we want the derivative of e to the ln of x times k. Okay, but we have e to the something, and we said that the derivative of e to the something is the same e to the something, but we need the chain rule. So times the derivative with respect to x of what's in there, which is the ln of x times k. Okay, and shall we put brackets around them? Yeah, just in case you think that. Okay, however, that k is a constant, so we can take it out. Let's go to the next line. Take it out all the way to the left. And then we have this, which we said, oh, wait a minute, that's the same thing as x to the k. So we have the k times x to the k times the derivative of ln of x. So let me keep that, and we already took the k outside. All right, but one more time, what's the derivative of ln of x? So we saw, reminder, it is just 1 over x. Okay, so x times x to the k, k times x to the k times 1 over x. Ooh, but we have x to the k times 1 over x, which is x to the 1. That's a quotient. So we said that you simply subtract the exponents. Okay, so you get x to the k minus 1, and that is exactly what we have in our formula. Okay, so let's go back to our friend x to the power square root of 2. What is its derivative? Okay, so we want the derivative of x to the square root of 2. So according to our formula, you just drop the exponent, square root of 2, and bring back x to the k, but subtract 1 in the exponent. Okay, so just for emphasis, let me put the times symbol there. Okay, and we have a minus 1. Square root of 2 minus 1. Okay, so that is the derivative of our x to the square root of 2. All right, for our grand finale, we are going to go a little bit crazy, and we are going to put our variable both in the base as well as the exponent. Okay, so in 5/3 to the x appears only in the exponent. In x to the square root of 2, x appears only in the base. Okay, so what if you have an expression like this, where x appears both in the base as well as the exponent? Okay, so we said that for these functions, x has to be positive. Okay, so we want the base to be positive in these kinds of expressions, and we just have to make sure that the exponent is also a well-defined number. Okay, it can be negative, can be positive, but it has to be defined. Okay, so we have cosine of x quantity to the power square root of x. Okay, let's find an interval where a function is defined. Okay, all we want is one interval. Okay, well, we have square root of x in the exponent, so that actually gives us a hefty restriction on x right out of the right at the bat. So x has to be positive. Okay, but cosine of x is sometimes positive, sometimes negative. Okay, so yeah, when we did the inverse trig functions, okay, we said that, okay, from 0 to pi over 2, it's positive, and then it becomes negative. Okay, so I think it looks like if we just restrict our function to 0 to pi over 2, then it's going to be defined. Okay, it can't be exactly 0. Is Maple going to object? Maybe, maybe not. Okay, so let's go to Maple and see what does this even look like. Maple will probably find other intervals where the function is defined. Okay, so let's see if GeoGebra freaks out over this. So we want, I'm going to put parentheses, okay, cosine of x raised to the power square root of x. Okay, so I called up the keyboard over here because that's where the square root symbol can be found. So there's square root of x. What's going to happen? Ooh, check it out. So what did I tell you? Okay, 0 to pi over 2, that works. That's fine. Okay, there's nothing though. Yeah, pi over 2 is about 1.5, right? 3.14, so 1.57. Yeah, that makes sense. There's nothing though between pi over 2 and 3 pi over 2. Okay, 2 pi is right over there. Okay, so yeah, GeoGebra is going to try to plot as many points as possible. Okay, so this is what cosine x to the power square root of x, what it looks like. Okay, so yeah, what would happen if we plug in pi over 4? What is f of pi over 4? Ooh, it's about 0.74. Okay, so yeah, let's plot it. Pi over 4, comma, 0.74. Yeah, that's the point right there. Okay. Okay, now that we know that it is defined in at least one interval from 0 to pi over 2, we're going to look for its derivative. Okay, so for that, we are going to need the process of logarithmic differentiation, which we introduced at the end of our earlier video where we saw the natural logarithm function. Okay, so we have y as a function of x, and this works only if we can apply the three properties of logarithms. We have a product rule, a quotient rule, and a power rule. Okay, it doesn't work on sums or differences. Okay, it's only a tool. Like all tools, use it only when it's appropriate. We will take the natural logarithm of both sides of y equals f of x. We will expand the right side using the three properties I just mentioned. So product turns into a sum, quotient turns into a difference. Power, you drop the power out of the logarithm. Okay, then we will apply the derivative to both sides of that equation. Keep in mind that you will need implicit differentiation on the left when you take the derivative of y with respect to x. Okay, so we will let y be this exponential expression. Take the ln of both sides. Ln of y is ln of cosine x to the square root of x. And we saw that this, from the graph, we saw that this is always positive. Okay, so we can plug it into the ln function, and according to our properties, the square root of x goes out, down it goes, and we are left, we multiply by ln of just cosine of x. Okay, so you might be thinking, shouldn't we subtract 1? No. That's a derivative formula. We're not taking a derivative. We're simply applying properties of the logarithm. Okay, so the exponent goes out. You just have ln of cosine of x remaining. Okay, but now we are multiplying two functions of x. Okay, you have a square root of x multiplied by ln of cosine x. Okay, so we are now ready to take the derivative of both sides of this equation. Okay, so I will put ln, d by dx, on the left and on the right. On the left, we have ln of y. On the right, we have square root of x times ln of cosine x. Let's put brackets here. Okay, so we are taking the ln of that product. We're taking the derivative of that product. Okay. On the left, we will need implicit differentiation. The derivative of ln of something is 1 over something, and then chain rule, we need the derivative of that something. So we get 1 over y times the derivative with respect to x of y. The something is y. Okay? So we get our dy by dx. Okay, so that should look familiar to you by now. That should be almost automatic. Okay. So on the right, we need to apply the product rule. Okay, so you can do it in any order. You can take f prime times g. We shouldn't use f and g because that's the name of our function. Take the derivative of this first. Yeah, why do we do that? Okay, so take the derivative of square root of x, and then we will multiply by ln of cosine x plus x times the derivative of ln of cosine x. Okay, and we have this. Okay, I guess we don't need a bracket for that. Okay, so now we can apply the power rule to square root of x. Okay, so yeah, it's basically back to basic calculus. X to the 1/2, so we drop the 1/2, we get 1/2 x to the 1/2 minus 1, negative 1/2, and then you multiply by ln of cosine x, and you have plus square root of x as the derivative of ln of cosine of x. Let me scoot up here. Ooh, we have another ln here. So again, the derivative of ln of something is 1 over that something. So we get 1 over cosine of x times the derivative, chain rule, the derivative of cosine x. Okay, so let me explicitly put down that step. Times the derivative of cosine x. Okay, so just to see, where did that come from? The chain rule. If you don't know where something came from, it's almost always the chain rule. Okay, so what do we have so far? We have this on the left, and on the right, we have this, and then we have one more step. The derivative of cosine is negative sine. Okay, so we can copy all of this up to here, and then you multiply the last step by negative sine, which we can put up here. There you go. Negative sine of x. Ooh, why did I put it up there? I hope you recognize sine x over cosine x. Of course, that's just the same as tangent of x. Okay. But also, oh look, we have an x to the minus 1/2 over here. So we can put that in the denominator as 1 over 2 square root of x. So we have a square root of x over here. Yeah. Yeah. And then we have a minus sign over cosine. So let's put the minus out here. And this just becomes tangent of x. Okay, excellent. And maybe as a final step in our simplification, let's put a common denominator. Okay, so we'll factor out the 1 over 2 square root of x, and we will put these together. But now we have square root of x here. We have to multiply by 2 square root of x, so we will get 2x times tangent x as our second term. Okay, so there we go. We have 1 over y dy by dx is 1 over 2 square root of x times the quantity ln of cosine x minus 2x times tangent x. Okay, so we now can solve for dy by dx, bring the y over to the other side. Okay, so dy by dx equals y times, big bracket, 1 over 2 square root of x, and so on. Okay. What is y? Oh, wait a minute. Y is over here. Okay. So we can write down our final answer. This is all 3 products, y times this times this. So we don't really need that big bracket. And that y we will replace by our original function. And it can go in our numerator. All right, there we go. So that is the final derivative of this function. It looks perfectly simple and innocent, right? It's just cosine to a square root. Big deal. Can't be complicated. Oh, yes, it is. And that is because x is both in the base as well as the exponent. All right, so it looks like that was our longest video so far. Hopefully it won't get much longer than this, and the next videos will be a lot shorter. I thought of cutting it into 2 parts, but I thought, yeah, let's all do it. You know how to use the pause button, right? Okay, so I hope you enjoyed that video. I hope you learned a few things, and I will see you next time. But until then, I hope you enjoy the rest of your day. Bye. Just kidding. There was a mistake over here. No.